Hello guys, welcome you all to this video. Here we will cover countability, particularly for net point of view, because as you know that 4.75 marks every year they ask from countability's part, so it is very important. And if you have proper understanding of the basics and the properties, then you can immediately solve the questions asked from this section. Okay, so let's get started with this. First of all, I'd like to give you the idea for equivalent sets. One thing, watch the videos regularly, but also follow textbooks. That is most important thing for the preparation. When we study textbooks, lots of examples comes in our hand and we can relate our understanding with all these things. Okay, that's why I highly recommend that never ignore this study. Okay, if you are a self-preparing candidate, then I am again telling you that never ignore the textbooks. That's the key. So, equivalent set. Suppose we have two non-empty sets A and B, and we call these two sets as equivalent set if there exists f from A to B such that f is a bijection. Then we call these two sets as equivalent set, and symbolically we define it or denote it like this way. And as a consequence, what we have is cardinality of these two sets are same. So when we have two sets as equivalent set, immediately we should think, or the thing come in our mind, that their cardinality is same. It is always true for the case of finite as well as infinite cases. Okay, fine. Now we are moving on to a very beautiful idea. With this knowledge of equivalent set, we are moving on to very beautiful idea for infinite set that will help us to understand the concept of countability in a very broad sense. So the story begins with the hypothesis of Cantor, a very famous mathematician. Cantor, also known as father of set theory. He proposed in the year 1907 that the set natural number, integer number, rational number, these three sets have same number of elements, and the set real number and the set complex number, these two have same number of elements. That is, their cardinality is going to be same, and the cardinality of R equal with the cardinality of C. In fact, in his second hypothesis, he proposed that cardinality of R and C is going to be greater than cardinality of natural number, rational number and integer set. Okay, but you should keep this thing in your mind, that Cantor's hypothesis, cardinality of these three sets and cardinality of R and C, these are going to be same, and cardinality of last two sets going to be greater than cardinality of first three sets. Okay, in fact, by this hypothesis, what actually we have, it is the comparison of infinity that we will study in the subsequent videos. Okay, fine. Now just a flavor I want to give you how the things work, like how the cardinality of n and cardinality of z are same. Observe it carefully. N, that is 1 2 3 4 5 so on, and z means -3 -2 -1 0 1 2 3 and so on. Okay, immediately one thing should come in your mind, that natural number set is a subset of z. So how it is possible? Being a subset of z, we are claiming that these two the same number of cardinality. It is contradictory statement for the case of finite set, but for the case of infinite set, this is, you can say, a beautiful property of some infinite cases. Okay, so for the case of finite set, this sort of property never hold. That is, one set is a subset of another one, and the other hand these two are same, it is never hold. But for the case of infinite set, it is not in generally true for all infinite sets, but it is true for some infinite set, and this is an example. How? If we map 1 goes to 0 like this way, and 2 goes to 1, 3 goes to -1, 4 goes to 2, 5 goes to -2, 6 goes to 3, 7 goes to -3, like this fashion, every element of z will be mapped with every element of n, that is 1 1 and onto correspondence is there. We can never ignore this 1 1 onto correspondence. So by our previous discussion, these two sets are going to be similar set, and their cardinality is going to be same. Okay, by this similar kind of logic, you can immediately show that set of natural number, it is going to be equal with set of the cardinality of set of natural number, it is going to be the cardinality of the set of all even integers. Okay, so this was a very beautiful property observed by Cantor. Okay, fine. In the case or in the study of countability chapters, we are only you can say interested to the existence of such function. We are not always interested in the explicit form of the function. Okay, so in this particular chapter, this is not a matter of concern that how the function looks like, but the thing is whether there exists such function or not. That is the matter of concern here. Okay, so with this understanding, we are now in a position to start with some basic definitions like finite set, then denumerable set, after that countable set. And many more things are yet to come. Say finite set. First of all, when we call a set as a finite set, that is, one possibility is either it is empty, another possibility is that all the elements of that set, suppose we are considering a set S, all the elements of that set will be mapped in some fashion with the elements of Jn, where n is some positive integer. Okay, that is, S is equivalent with Jn. Then we call that set S is a finite set. Suppose, for example, I am taking S as a set of, say, A, B, C. So in that case, we can take J3, 1, 2, 3, and it is very much clear to you that a 1 onto correspondence, it is always possible. So it is, you can say, a finite set. Fine. For the case of denumerable set, suppose S is a set and we call it as denumerable set. In that case, S should be equivalent with N. That is 1 onto correspondence should exist between the set S and N. Okay, that is denumerable set. That means every element of that set S should be enumerated in some fashion to the set of natural number. For example, I am taking S as say X, Y, A, B, C, D, suppose T, M, and so on, a random fashion. Okay, but N is there, so 1, 2, 3, 4, 5, 6. Immediately what we can do, that just map like this fashion, X to 2, Y to 3, A to say 1, B to 4, like this way, and that will give us that one mapping with A, that is enumerated by X1, then 2 to X, so enumerated X2, 3 to Y, so it is X3, it is B, so we enumerate it by X4, and like this fashion, look at, we can enumerate every element of the set of S. Okay, so this is example of a denumerable set or enumerable set. So another terminology is enumerable set. Okay, so these two were finite and enumerable or denumerable set. So if one of these two hold, suppose S we are considering a set, non-empty set. Okay, S, if S is either finite or denumerable, then S turns out to be a countable set. Okay, that is the basic idea for a countable set. Now, for your understanding, I would like to give you one question here, and let me know in the comment section that what will be your answer. Which of the following is true? Statement 1, every countable set is finite. Statement number 2 is every finite set is countable. Let me know in the comment section that what is your answer. And this was for today's video, and I will not extend it too much because that 13 or 14 minutes video, it is small, but when you go to the textbook, it will take at least 1 to 2 hours to grab the concept if you are new to this field. Okay, it can take more than 2 hours as well. Okay, so just to go to any one of the recommended textbook and try to read more and think more with some examples, and also don't forget to give the answer in the comment section. Okay, thank you and meet you soon in the next video.